Induction motor drives. In present scenario, induction motor drives are the most mature technology among all other types of commutator-less motor drives. There are two types of induction motors, the wound rotor type induction motor drive and squirrel cage induction motor. Because of high cost, need for maintenance, and lack of sturdiness, the wound rotor induction motor is less attractive than the squirrel cage induction motor, especially for electric propulsion in EVs. Because whenever it is the wound type, it has the winding, it has the stator winding, it has the rotor winding. So instead of that, the squirrel cage type is more popular. The squirrel cage induction motor is loosely named as also the induction motor for electric vehicle applications. In addition, the common advantage of commutator-less motor drives, the induction motor drives possesses the definite advantage of low cost and sturdiness. These advantages are generally outweigh their disadvantage of control complexity and facilitate this technology being widely adopted for electric vehicles. This is the basic configuration of induction motor drive. There is the induction machine. Now the voltage, current and positions, these are given and sensors are providing this input to the controller. Controller also will have the command signal as per the requirement to increase the speed or torque. Based on this, the signal will be given to the PWM inverter and the suitable output of the PWM inverter will be given to the induction machine. Here, dual motor configuration of induction motor drives for electric vehicle are shown. The single motor configuration and dual motor are shown. Here we can see the single motor configuration where there is induction machine, there is a fixed gear, and as single machine is used, a differential is used, that is a differential gear, and it is connected to the wheel axles. So the propulsion is through a single induction machine and with fixed gear and differential. In dual motor configuration, as we can see here, the first configuration is the high-speed geared structure. So here is wheel, and this is the induction motor attached to this wheel with a fixed gearing arrangement. So there are two induction motors attached at two different wheels, maybe front driven or back driven. And we can see the second low speed gearless structure. So here induction motor is attached directly to the wheels and the fixed gearing arrangement also removed. So this is the further efficient configuration because of removing the fixed gear from the system. If you see the structure of induction machine, it has the outer frame, the stator core and stator winding, which is placed into the stator slots. There is the rotor. Now, based on the type, it will be wound type or it will be squirrel cage type. The wound type will have its winding on this, and squirrel cage will have solid bars on this rotor. And then there is a bearing and shaft, and also there will be the fan for the cooling purpose. Now we can see this is a basic induction machine topology. So there is the outer stator, inner is the rotor. These are the rotor bars. If we consider this is the squirrel cage induction motor. Here are the solid bars. So the sturdy construction. This is the shaft, and this complete assembly is the rotor. Stator winding can be the three-phase winding. Now this is the inner rotor. Rotor is inside, stator is outside. There may be outer rotor induction machine topology, where the inside there is a stator which is fixed, and outside there is a rotor. Here you can see the winding is there, and here there are the solid bars, rotor bars. So this type of construction generally we can observe in the ceiling fans, which is the outer rotor, and to this outer rotor the blades are attached. Principle of working of induction motor. The basic requirement for induction motor to produce the rotating field, a three-phase winding is required with a phase difference of 120 and 240. There is a three-phase difference, and it should produce the three-phase currents into it. And these currents can be given by this equation. Current for phase A, phase B, and phase C, that is Ia equal to Im sin of omega t at the reference, Ib equal to Im sin of omega t minus 120, that is 120-degree phase difference, and Ic is equal to Im sin of omega t minus 240, that is a 240 phase difference. The stator MMFs, that is a magnetomotive forces, will be produced by this phase currents, and this can be again stated. The magnetomotive force Fa is equal to Fm into sin omega t. It is varying in the sinusoidal way. Fb is equal to Fm sin of omega t minus 120, and F is equal to Fm sin of omega t minus 240. So with this, a rotating magnetic field is produced, and this rotating magnetic field will link to the rotor conductors. Now stator, there is a stator winding, three-phase supply is given, then rotating magnetic flux will be produced because of this phase difference, and it is revolving at a synchronous speed. It may be 1500 rpm, for example. Now this flux cut the stationary conductors. Now because of this, the stationary conductors are placed into the vicinity of the flux, which is again the revolving flux, and because of this, the conductors cut the rotating magnetic field, and EMF is also induced into it. Now these conductors try to oppose the very cause of producing the EMF into it, and that is the rotation. So the rotor will try to rotate with the speed of rotating magnetic speed to reduce the relative position between it, and thus it will remain in rotation, and it will never catch the electromagnetic field, and that is there is certain difference into the speed of rotating magnetic field and the rotor speed. Thus it is the slip. Here you can see the flux, force, and the direction of the current. The application of induction motor drives in electric vehicles. The Ford Siemens electric vehicle motor was one of the most well-developed induction motor for electrical vehicles. It was a three-phase water-cooled induction motor with output power of 33 kilowatt and 67 kilowatt peak and weight about 65 kg. The motor was targeted for rear-wheel drive, in which the gear reduction and the differential were integrated with the motor. This motor and its derivative were successfully applied to different modes of electric vehicles, such as the flagship EV of Ford Motor, that is Ford Ranger AV. Ford Ranger AV was a pickup truck which was powered by 6-pole induction motor drive that could achieve maximum speed of 13,000 rpm while equipped with 3:1 single-speed gear reduction. Showcasing the most advanced propulsion system in 1997, The EV1 was the flagship EV of General Motors. It was front-wheel drive electric sports car which adopted a three-phase induction motor drive and a single-speed transaxle with dual reduction of 10.95 to s to 1. Offers torque of 149 Newton meter from 0 to 7,000 rpm and a propulsion power of 102 kilowatt from 7,000 to 14,000 rpm with a top speed 128 km per hour, an acceleration from 0 to 96 km in less than 9 seconds. While customer reaction to EV1 was positive, EV1 was expensive, so General Motors decided to terminate its production in 2000. The introduction of high-performance electric sports car at the San Francisco International Auto Show in 2006. The Tesla Roadster exhibited its streamlined body and outstanding performance. Tesla Roadster was produced by Tesla Motors between 2008 and 12. It adopted three-phase four-pole induction motor drive to produce a maximum power of 215 kilowatt, maximum torque 400 Newton meter, and maximum speed of 40,000 rpm. It weighted less than 32 kg and delivered an average efficiency of 90%. The whole EV weight was about 1200 kg and it was a rear wheel drive. Equipped with a single speed fixed gear transmission of 8.20 s to 1. It could offer acceleration from 0 to 96 km in 3.7 seconds and top speed of 200 km per hour. It was installed with a lithium-ion battery of 33 kWh. It could run 393 km per charge based on the US Environmental Protection Agency combined cycle.